All right. So today is lecture 17, and we're gonna kind of continue talking about Gauss's law, and then half the lecture, I think we should finish Gauss law and then talk about the next important topic, which is potential and potential energy, which is something that you have seen already in physics 1, but this will be in the context of electrical potential energy, right? So that's kind of the plan for today. If we have even some time left, then we're gonna start talking about capacitor. But if not, then we're gonna do that in the next lecture. Okay, so let's review what we talked about last time. So last time we introduced Gauss's law, and what it says is in terms of like equation or formula, it says something like this. So the total electric flux, okay, which we use the symbol phi subscript E, is equal to the charge inside divided by a constant which is called epsilon 0. So this is pronounced epsilon 0, okay, which is a constant. It's a fundamental constant in physics. So in other words, just a number. So it's not probably as important as the other thing, which is the Q inside here. So what this means, so this is what we call the Gauss's law. So the way to use this is this. So first you need to decide the Gaussian surface. So you need to decide what you're going to be used as a surface for this Gauss law. For example, the easiest case is if you have, like some charge here, let's say plus small q here, and then you are absolutely free to decide what kind of surface you want, what the shape you want, how big it is, how small it is, doesn't really matter. You just have to pick one, okay? So I gotta pick one kind of randomly. So I gotta pick the one that looks something like this. So it's a three-dimensional surface. So 3D surface, and it should be closed surface. The reason why it's closed because we should be able to define what's inside this surface and what's outside, right? So the reason why we need it closed is to be clear what's inside or outside the surface. Okay, so if the surface is not closed, for example, the surface is like kind of like a coffee cup or something like this, right? Maybe it looks something like this, a coffee cup, right? It's kind of hard to say which is inside, which is outside, because if you can say like this point here is inside, it's actually connected to the outside world through like the opening, right? So that's not good. So you need something which is closed, and it should be no ambiguity at all, what's inside and what's outside. All right. So that's what I mean by a closed surface. So the surface that you choose has to be closed, and of course it has to be three-dimensional because we live in a three-dimensional world. All right. So once you decide what surface you want, and again, you can use any surface that you want. Um, so what kind of surface to choose, it depends on the problem. And picking the one which kind of, useful to the problem is obviously going to be better than just pick some random stuff. right? So we're gonna see a few more examples today, right? But anyway, once you pick the surface, right? So you have to just count. So that's gonna be step number 2. So once you decide what surface you use, and we're gonna call that a Gaussian surface. So essentially what it means is it's a surface that we're gonna apply Gauss's law to that surface. Okay. So number 2 is to count the amount of charges enclosed by the surface. Right. So essentially, enclosed by the surface means it's the amount of charge which is inside the surface. Right. So if your surface is something like this, maybe it's like a balloon, and inside this surface you have plus q, then that's going to be the charge enclosed. And that's what it means by q inside here, right? So count the amount of charges enclosed by the surface. That's what we call q inside. Okay, that's q inside in the formula. So what about the case where you have multiple charges inside the surface? For example, you have plus q here. You might have another one which is minus q. And then you have the third one which is also plus q. Well, you just need to count all of them. And the sign also matters. So this is plus q. Another one is minus q. So q inside is 0. And then another plus q here. So in total, q inside in this case is just plus q because one of the minus q cancel out the plus q, right? So you just counting number with like plus and minus sign applied to each charges, right? And you count only the one inside. So if you have a lot of charges outside, like 2q here, 3q here, and another plus 4q here, right? So the charge outside doesn't really matter. You don't care. You only care about the charge inside, right? So that's what we mean by q inside, right? So it's really just the charge inside. All right, so once we have that, then we just say the Gauss's law, which is the total flux. So I can write, so it's actually probably better if I write it this way. So electric flux total is equal to just q inside divided by epsilon 0, right? So this is fine, we know what it means. And this epsilon 0 is a constant, so it's just a number. So this one is the total electric flux through the surface that you chose in the first step. Okay, so it's the total electric flux, which is electric field times the area through the surface that you chose. Okay, so the total electric flux depends only on the charge inside. So it means that if you have multiple surface and they enclose the same amount of charge, then the total electric flux through the whole surface, maybe I should add that, through the whole surface, will be equal because it depends only on q inside here. All right, and last time we applied this to a case of infinitely long wire, and we found the electric field equal to the result that we got earlier in the last lecture from direct integration. Okay, so we're not going to repeat that, but after today's lecture, if you go back, I hope that you understand that example a little bit more. So today we're going to look at a few other examples, and the first example is actually just to reproduce the fact that we already know. All right, so we're going to look at a point charge. Okay, a point charge. So, and we're gonna kind of calculate the electric field at some position from a point charge, and then you're gonna see that using Gauss law is actually agrees with what we know already from Coulomb's law. So how do we do that? Well, let's say we have a point charge here plus Q. Okay, and we want to know the electric field at this point P here. So I want to know what is electric field, so vector E at point P. And we kind of know already what it is. All right, so let's pretend we don't. So we want to apply Gauss law to this. So how do we use that? Well, first, remember, we need to decide what kind of Gaussian surface we use. Right, so we need to decide the shape of the surface that we're going to use for the calculation. Now, what kind of shape you decide to use depends on the symmetry of the problem. So in this problem, the symmetry of the problem is what we call spherical symmetry, meaning that it probably doesn't matter which point P you choose as long as point P is the same distance away from the charge, right? So as long as the distance is the same, no matter where you are, the electric field should have the same magnitude. So that's the symmetry that we are talking about here, right? So if that's the case, then the Gaussian surface that we choose should kind of preserve that symmetry, which is spherical. So the surface which is suitable in this case, it also should be spherical surface, right? It probably doesn't make sense to define a surface which is like a cylindrical, something like this, because I mean clearly this problem doesn't have this kind of symmetry, right? Unlike the problem of like a straight wire that we did last time, and that one has this kind of cylindrical symmetry. We don't have that here, so we should instead construct a surface which is spherical, and in two-dimensional is essentially just a sphere or a circle, like looks like this. Okay, so that's the first step. So the first step is to define or construct a spherical Gaussian surface. And again, so we chose this because our system has a spherical symmetry. Okay, so that's why we chose a circle or a sphere to be the Gaussian surface. Okay, so that's the first step. The second step is to count how much charge we have inside. Well, in this case, easy because it's just one. So Q inside is just plus Q. Okay, so there's nothing kind of crazy here. Right? There's only one charge, which is plus Q. So the Q inside, Q enclosed by this spherical surface or a balloon is just plus Q, right? And then the last step is to write down the total flux, right? Because the last step is the total electric flux total is just Q inside divided by a constant epsilon 0, but Q inside is just plus Q. So we know already the right-hand side of this equation. The other thing that we need to work on a little bit is the left-hand side, which is total electric flux, right? And the electric field from a point charge will point away from the charge. That's what we know already from, like Coulomb's law. So at any point on the surface, for example here, the electric field will point that way. Mathematically, we call this one to be radially outward, right? So electric field is pointing radially. So this one point radially out, right, from the charge plus Q. Right, radially means in the radial direction. So that means if you pick a different point, let's say like here, then electric field gonna point this way, right? So it's always pointing in the direction along the line joining the point that you're interested in, which is here, and the charge itself, right? So that's true for every point on the surface. And remember why that's the case? Well, that's because we chose the surface to be spherical. So that's why this is true, okay? If you choose, again, the surface which is not spherical, for example, you choose the surface which is, a little bit, well, even something like this, right? There's nothing wrong with this, okay? Gauss law still applies, but it's not so useful because at any point on the surface, the electric field will point kind of in this way, which is not kind of perpendicular to the surface, right? So it works, but it's not quite useful for us in order to calculate what the electric field is, right? So a spherical, again, is a very suitable choice in this case. All right, so what's next then? Well, the electric flux is the electric field. I need to go to the other page. So let me draw this again. So the electric field of plus Q at this point this way, which is perpendicular to the surface, right? So because this is a sphere. So the total electric field, total electric flux is the electric field dot with the area, okay? So in this case, every point on the surface, the area is perpendicular to the surface, but because this is a sphere, the area is always pointing in the same direction as the electric field. Okay, so a spherical surface means that a vector A is always in the same direction as the electric field, no matter where you are on the surface. Okay, this is a result from our choice of a spherical surface. So this dot product becomes something which is very easy to deal with because you don't need to put in, like the cosine of the angle or something like that, because that angle is always 0. So in this particular case, it's just electric field times the area, right? So all this together, electric flux total equal to electric field times area equal to Q inside, which is plus Q divided by epsilon 0. And what is the area of this sphere? Well, the area or the surface area of this sphere is 4 pi r square, right? Where r is the radius of this surface. So it's 4 pi r square, 4 pi r square equal to plus Q divided by epsilon 0. And rearranging this, we have the electric field, or at least the magnitude of the electric field, to be 1 over 4 pi r square plus Q divided by epsilon 0. And then rearranging this a little bit to be in a familiar form is 1 over 4 pi epsilon 0 times plus q divided by r squared. And you probably guessed already that this is the same as what we have in the previous lecture, which is the electric field from a point charge is just kq divided by r squared. Right, so you can see that the constant k, which is the electric constant, is actually the same as 1 over 4 pi epsilon 0. So it's just a different way of writing the constant k. But you can see that the 1 over r squared dependence, or the dependence on the electric field, is the same in this case. Right. So using Gauss' law, you actually reproduce the result that you got from Coulomb's law. Okay, and the thing here is that this line here, this line only tells you the magnitude of the electric field, right? Because we are talking about flux, and flux is the dot product between electric field and area. So the kind of like the how should I say, like the vector, like being like electric field is a vector, like that kind of like being a vector is actually doesn't survive this dot product, right? Because it's a scalar, right? So in the end, you only have the magnitude of the electric field, which is what we expect, right? But we know that electric field is a vector, so you also need a direction. So how do we get that information? You don't get that directly from Gauss' law, but you get that from the way you construct the Gaussian surface in the first step, right? So it's kind of like indirectly infer that, okay, due to the symmetry of the problem, electric field is pointing radially outward. So that's kind of how you know what the direction of electric field is. Okay, so that's something to keep in mind. In any case, this gives you the same result as what you got earlier from Coulomb's law. So it's probably not as useful to use Gauss' law here. But we're going to look at a different case, which is more, I think, useful, if you may. Right. So let's talk about a spherical charge conductor. So what are we talking about here? So instead of a point charge here, we're going to consider an electric field from a spherical object. And it's not just any object, it's a spherical conductor. So maybe a copper ball or a silver ball, which made from metal, and it's shaped in a spherical way. So maybe something like this, right? So a spherical charge conductor, so it's a sphere made from metal, and let's say we put in a charge plus Q onto this object. Right. So at this point, you should know right away that, okay, it's a charge conductor. So that means the charge plus Q that you put in must be evenly distributed along the surface of this charge conductor, right? Remember that any charge that you put into a conductor, the charge will be at the surface. Okay, always the case. Right. So once you put that in, this charge plus Q will get distributed along the surface, something like this, right? And the total charge is plus Q again. Right. So if you have a large object, then the charge density might be a little bit less because you have more surface area for the charge to leave. But anyway, the total charge is plus Q like this. And we ask the same question, which is, let's say we are interested in this point P here, which is a distance r away from the center of this object. What is the electric field at point P, so EP. So what is the electric field at point P? Right. If we don't know already the answer, it's actually not quite easy to answer this one. Because in order to answer this question, the only thing that we know is that the charge, the electric field from a point charge is given by this. So E equal to KQ divided by R square, or the magnitude of E is like this. This one is for point charge. So anything other than point charge, you have to integrate it the same way that we did in the last lecture. So there's a lot of work to do, right? And usually the way to do is to, like divide this sphere into, like a strip, like you peel like an orange or something like that, and calculate each strip with some charge, and then you have to add them up in the same way that we did last time, which is mathematically quite difficult to do. So is there an easier way to do that? Well, the answer is yes, because this is also a perfect place to apply Gauss' law, right? So compared to what we have in the previous example, in the previous example we have a charge, which is a point charge, right? And then we say we choose a sphere as our Gaussian surface because that's the symmetry of the problem. Now looking at this one, you have the same symmetry because the object, even though it's not a point charge, is still a sphere, right? So you still have this spherical symmetry. So what I can do is I can create a spherical object, spherical Gaussian surface. So I'm gonna change it a little bit here. So I'm gonna create a Gaussian surface which I chose it such that point P is exactly at the surface of my at the surface of my sphere. Okay, so again, this is step number one. So we choose a sphere as a Gaussian surface. Right. Okay. Well, I mean, strictly speaking, a sphere is not a surface, so I should say, spherical surface. But I mean, you know what I mean. So I chose a spherical surface to be my Gaussian surface here. So that's my first step of applying Gauss' law. All right. And then what's the second step? Well, the second step is to, so this is step number one. Second step is to count how much charge you have inside this Gaussian surface. And that's also pretty easy because the only thing which is enclosed by this surface is this much charge, which is plus Q. Right. So Q inside is still plus Q, right? Exactly the same as what we had in the previous example, right? The only difference is how the charge is distributed, right? The previous one is a point charge. In this one, is distributed along this blue sphere, but the total charge is still the same. All right, so Q inside is still plus Q. But then the last step is to calculate the electric flux, so E total equal to Q inside divided by this constant epsilon 0, right? And because we have the same symmetry, we apply all the reasoning that we did again in this question. That means we know that electric field at point P must also point radially outward like this. So if you choose a different one, maybe this one, then electric field will also point that way. Right. It has to be like this because otherwise it doesn't obey the symmetry of the problem. So think about this. If you say, okay, the electric field at point, which is here, it doesn't point radially outward, but it point that way. Okay, so maybe some of you say, why can't it point in that direction? Well, the reason is that if you choose the electric field to point in direction, well, why not this direction then? Because there's no reason that the electric field will have this preferred direction to point to the right. So it might as well point to the left, right? So you have this kind of like something that you cannot decide because, I mean, it's not clear like why one is preferred than the other one. And that's because you are kind of like violating the symmetry of the problem, right? The problem has spherical symmetry, so the electric field must also obey that symmetry. And the only way it can do that is for the electric field to point radially outward, right? So that's why every point on the surface, the electric field must point radially outward from the center of the sphere, like this. Okay, so that being said, the electric flux, again, is just E dot A, which is the area, electric field times the area. And the area at the spherical surface will also point radially outward because it has to point perpendicular to the surface, right? And the sphere, the area is always perpendicular to the radial direction. So E dot A becomes just E times A again because cosine of 0 is 1. So you have the same thing, which is E times the surface area, which is 4 pi r square. And that's equal to Q inside, which is plus Q divided by epsilon 0. So this might or might not surprise you, but the answer is the electric field from a spherical charge, okay, not the point charge, a spherical charge actually has the same formula as the point charge. Okay, so electric field E field from a spherical charge is the same as E field from a point charge. That's what we got here. Okay, so this is very nice because you got this result from applying Gauss law. It's a lot easier than like dividing this sphere up into multiple strips and you have to integrate it. That's a lot of calculus to deal with, and we don't really want that if we don't have to, right? So this is a case where applying Gauss law is very, very good because it saves a lot of work. And it's a very important result because you're going to see this quite a few times, is that the electric field from a sphere, right, not a point charge, a sphere, it actually have the same formula as the electric field from a point charge. So is there any difference between a sphere and a point charge? Well, the electric field is the same, right? So does that mean they are completely, equivalent to each other? Well, not really, because the sphere that we use as the Gaussian surface, the red sphere here, we construct it so that it's outside the blue sphere here. If we construct the red sphere to be inside the blue one, then things will be different. So let me show you what I mean here. So again, we consider a spherical charge where all the charges are at the surface, right? And we know this because this is the conductor, right? Just to remind everyone that it's the conductor, so the charge will be at the surface. But now, let's say you construct a surface for Gauss law inside the sphere. And why do you want to do that? Well, because you want to see what's the electric field inside the sphere. The electric field that we calculate here, this is E outside the blue sphere. So it's E outside the sphere charge. Right. So outside the spherical charge, the formula is the same as the point charge. But what about electric field inside? Well, electric field inside, you need to come up with the Gaussian surface. So this is the Gaussian surface. But now it's inside the blue sphere. So we can apply, so this is the first step. The second step is to figure out what is Q inside. And you should convince yourself that Q inside is 0. Because remember, all the charge is at the surface of the blue one. So if you draw the red one inside the blue sphere, then there's nothing here, right? It's completely empty, so there's no charge enclosed by this red sphere because all the charge is at the surface of the blue one, which is larger than the red sphere. So Q inside is 0. So Q inside is 0 means the total flux, this is applying Gauss's law, which is total flux equal to Q inside divided by epsilon 0, has to be 0. So that also means the flux here must also be equal to 0. And what is the total flux is electric field times area. We know that area is not 0 because we define the sphere, the red one, to have non-zero radius. So the area cannot be 0. So the only way this can be 0 is for this electric field to be 0. Right. So from this argument, so we conclude that the conclusion, the electric field inside a charged sphere is 0. Is this a surprise? No, because we knew already when we introduced the conductor that inside the conductor you cannot have any electric field. We know that already, and this just confirmed that. Okay, so if we were to plot the electric field of a spherical charge as a function of the radius, which is a distance from the center of the sphere. So let's say this sphere has a total of plus Q charge, and they are all at the surface. Okay, and we need to find the electric field, right? So outside the sphere, the electric field, so E outside, we have the same formula as the electric field from point charge. So that's going to be 1 over 4 pi epsilon 0 Q over R square. Or if you don't like 1 over 4 pi epsilon 0, you can just say K instead. Just to also save some space. Right, so it's K, it's the same K that we knew earlier, electric constant times Q over R square. Right. So that's true for any point outside. So this is outside. So that means the electric field will have this kind of 1 over R square dependence like this. But for electric field inside, so E inside, that's going to be equal to 0 because what we just did earlier. So electric field inside will be 0, like this, right? So if you plot the electric field, it's going to look like this, right? 0 inside until you reach the surface. Suddenly you jump to this value here. So what's the value that you jump to here? Well, that's the electric field outside where R here is the radius of the sphere. Right. So that E is KQ divided by R squared. And let's say big R is the radius of the charged sphere, like this. Okay, so it's quite a nice example of using Gauss law to calculate electric field. Usually the problem that contains some kind of symmetry will be good to use Gauss's law, because otherwise it's not quite useful. Right? For example, if you talk about charge which is plus Q and another plus Q here, and then you want to know the electric field, let's say at this point, P, right? Even though you can just write, okay, E here, and then you can just add them up. But let's say you want to use Gauss's law to calculate this. It's very difficult to do because what kind of surface I should choose is not so obvious, because I cannot choose a sphere, maybe an ellipse or something like that. But a sphere is definitely not good because it doesn't have that symmetry. Right, so you cannot say that the electric field everywhere on the sphere is going to be the same, because if you talk about this point here, it's going to be closer to this charge and further away from here. But if you talk about this point, it's going to be equally, far from each charge. So it's really weird to try to use Gauss law in this case. Okay, so Gauss law is useful, but not always. So it's kind of good to know like in which situation you can use it, in which situation is probably useless to try to apply that. There's one more example I want to talk about using Gauss law, and that's going to be important also when we start talking about capacitor. Right, and that is the electric field from a sheet of charge, so E field from a sheet of charges. So what it is, well, it's what it says is just imagine that you have a really large sheet of, let's say it can be metal, it can be insulator, whatever. But what you have is you have charges evenly distributed on this sheet of metal, like metallic paper or something like that. Right, evenly distribute something like this. Right, and what you can say is that okay, the density of charge is given by this. So this is a new kind of thing, but conceptually it's not too difficult to understand what it is. So we're going to define this parameter. This is sigma, right? So it's the Greek letter. It's lowercase sigma, so you probably are used to this sigma here. This is uppercase. We use this for summation, and in physics sometimes we use this small sigma as something which is related to the area. Okay, so it looks like number 6, but it's not. Okay, so be careful. So this sigma is the charge per area. So this is called the area charge density. Right, so the unit is coulomb per meter square, something like that. Right? Because usually we talk about the sheet of charge which is really, really large. is large enough so that we can approximate the sheet to be, like almost infinitely large. Right? So the larger the sheet, the more charge you have, right? So instead of talking about the total charge or the total area, it's a lot more convenient to talk about sigma, which is the charge density, okay, charge per area. Right? In the last lecture, we have linear charge density, that's charge per length. Right? So it's different geometry, different object, but the concept is kind of the same. So the, the problem we want to answer is this. So this is, let's say, a charge on a really large sheet of metal or something like that. And we want to know what is the electric field at the point above this charge, this sheet of charge. Right, so side view, it might look like this. So let's say you have a really large sheet of charge, and it's all going to be plus, 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 plus. Something like this. Okay, so this is side view. And we want to know what is the electric field at this point, which is just above this sheet. E field. That's what we want to know. And also below, but that's kind of the same question. Okay, so what is the electric field above this sheet? And again, you can use calculus to calculate this. You can, like divide the charge into different chunks, and then you can write the electric field from each chunk, and then you have to add them up. Right? So that's it's not too bad in terms of the mathematical procedure, but we want to avoid complicated calculation if we can, especially in this case where we can actually apply Gauss law. So we're going to do that. So how do we choose the Gaussian surface for this situation? So we're going to choose it like this. So sideways going to look like this. So this is our surface. And in kind of like a 3D drawing, it looks something like this. So it's kind of like a cylinder that goes through the surface. Okay, so I'm not good at 3D drawing, but this is what I'm trying to draw. Right, so the surface is also this one. So it's a cylindrical surface. So in other words, what I'm trying to draw is this cylinder where it goes through the sheet like this. Okay, so this is the sheet inside the cylinder, and this lid is here, this lid is here. Right, so hopefully this is clear enough to understand what I'm trying to do here. Okay, so this red cylinder is my Gaussian surface. And I draw it like this. So I draw it such that the lid area is given by small a. Right? This is kind of chosen arbitrarily. It can be any other area, but I chose it to be a. And that's going to be true for the lid, which is beneath the sheet, right? So this blue one, this is the sheet here. Charge sheet. Okay. So looking at this cylinder, there are four surfaces, right? The top lid, the bottom lid, and the wall of this cylinder. So let's talk about the wall first. because of the symmetry of the problem, you should convince yourself that the electric field must be pointing perpendicular to the sheet itself, like this. Especially for a sheet which is infinitely long or almost infinitely long, right? Because if the sheet is infinitely long, you cannot tell left from right. So that means it doesn't make sense to have electric field pointing something like this. That's going to be really strange because if you say electric field is pointing like that, then I can say, oh, why not this direction then? Because you can just rotate the whole thing and you're going to get this. So in order to avoid that kind of, like paradox, if you may, the electric field must point perpendicular to the surface. So that means the electric field in the system will point this way and this way. So you can see that there's no electric field going through the wall of the cylinder. So no E field. Through the wall of cylinder. So that means the flux, electric flux through the wall of the cylinder must also be zero. Because the area of the wall, the vector is pointing that way, sideways. Okay, no matter where you are on the wall. If you are here, area will point that way. If you are here, then area will point that way, right? But no matter which way, where you are on the wall, it's gonna be always perpendicular to the electric field. Because electric field is always either pointing up or down. It doesn't have the sideways component. So that also means electric flux is also zero for the wall. And the only surface that you have non-zero flux is the top lid and the bottom lid. Those two only. So that means I can write the total flux. I'm applying Gauss law here. E total. That's going to be just the flux through the top and bottom lid, right? So that's going to be how much area we have. Top we have A, bottom we also have another A. So the total area is 2A. So the flux is just electric field times 2A. Again, we don't count the wall because the flux through the wall is zero. And that's going to be equal to Q inside. Q inside this cylinder is this area of the charge sheet, which is also small a, times the charge density, right? So the charge enclosed by this cylinder is small a times sigma, the charge density. That's going to give you Q, and divide by epsilon 0. So electric field is simply sigma divided by 2 times epsilon 0, like this. And you can see that the area cancel out, which is good. Because remember, the area is something that you come up with. It has nothing to do with the charge sheet itself, right? So the area A cancel out, which is good. And the other thing which is important is that electric field here, it also does not depend on how far away you are from the sheet. And it might be a little bit strange if you think about it. Like further away, it should be weaker in terms of the electric field. That's true if you have a charge sheet which is not infinitely long or large. Right? In this case, it's infinitely large, so it doesn't matter how far away it is from the surface; it's still, infinite. Right? So that's kind of the thing. But of course, like in real life, no sheet is infinitely large. So this is more like an approximation, but it's good enough in most cases, right? So to summarize, the electric field above or below, right? It's the same thing. Above the infinitely long sheet is given by this value, okay? Sigma divided by 2 times epsilon 0, okay? And again, this whole exercise just to demonstrate you that in some cases, Gauss's law is very convenient in determining the strength of electric field, right? Otherwise, you need to do a lot of integration, which is a lot of math, and that's not ideal, right? If we can avoid that, that would be great. Okay, so it's probably a good time to take a break now, and I'll be back in 10 minutes to talk about the next topic, which is potential. All right, so see you in 10 minutes.